Okay. So yesterday, in a little bit of quick manner, I explained about the design flow. Although I didn't explain, I said I would be explaining that, and that too in a detailed manner. So it is. These are the steps. These are very generic steps. I won't say that these are specific steps involved in designing of the chip, but definitely these are the major ones. Okay. So here comes the design flow in which it is divided into three stages. Okay. So the first stage is like front end. Okay. In which the design is made related to the application perspective. Okay. So it is in the front face of the application or the product. So that's why it is called as the front end design. So where any changes in the application or the code or the schematic will bring and changes related to aesthetics. Okay. So for example, let's take an example of your house design. For example, you're an interior architect, okay, or a designer, or let's say you are a person who wants to get his own flat design. Yesterday, we took an example of designing your own building. So this time you assume that I'm a little bit of degraded or downsized and I don't have enough money to make my own building, but definitely I can afford my own bungalow. So what I do is that I call some architects to design my bungalow. So how do we do it? So we take a piece of paper and we put everything on the paper. That okay, this is the number of bedrooms I want. Then how the layout should be, how many, what would the size of the bedrooms, or how many kitchens are required, how the storeroom would be. So you are only talking about the aesthetics of the front face of the building or the layout. So there you are not talking about anything, what kind of materials will be used or what kind of plot size or any kind of construction materials will be used. No, that is not relevant at that point of time. Okay. So these are all on pen or paper. So all about your description exactly are taken by the designer and he put into a design entry format. So he writes in the set of Verilog Diesel code or he makes into schematic and then puts into a description format. So this is called as, if we call, so this process is called as design entry. Okay. So once that is done, so that is converted to another file level netlist output, which is called as a netlist over here. Okay, so your design schematic or a Verilog file is synthesized and converted to a gate level netlist. Okay, so that is more understood by the softwares and they make an understanding of it. So let's, for that purpose, we need to remove this annotation and let me have a blank slide. I believe I'm audible, clear, and there are no doubts related to my audio. My speed, pitch, and volume, they are coming good. Okay. So, for example, you wish to make something of this kind. Okay. Okay. So this is what the design you wish to go for. So you write a design entry, right? You make a design entry. You write in the code, let's say this is P. Okay. So you say P equal to A and with B, Y equal to P and with C. That is your description of the code, right? So this is called as design entry, in which you describe how your design is going to behave or work. I will not talk about on the more descriptive levels of design entry like behavioral modeling, RTL modeling, all that stuff. But yes, all these ways are called as design entry methods. Okay, so this is whatever desired functions, features, they are put on the paper. Okay, it is just like the architect. He understands your design requirement and draws the layout on the paper. Okay, and now what he is using for the making the layout, it's irrelevant left, right. He's using a pen, pencil, plotter, whatever he can make use of it. Okay. So next in the stage is synthesis. Synthesis is a process where high level description is converted to a low level description. Okay. Just hold on, guys. Now, huh. So that means this is like this cannot be done without an library input. See here. Here, the input to the synthesis is a technology library file. So if you say that synthesis is my some design process, okay. So one of the input to the synthesis is your design file. Design file. The another input is your technology library. Okay, tech library. Okay. So based on that, the output of the synthesis is a netlist. Okay. Any doubt question on this? Now, what does this mean? This means that we asked him to make the gate for us, right? Right? Now I give this to my synthesis process. Now, based on the technology library available, the synthesis can do in many ways. He can do that, this. Okay. He can do this. He can do this. He can make use of he can do this. So what technology component is available, synthesis will use that and will make your Boolean expression possible. So it is totally dependent on what is the technology library file you're using. Okay, what kind of components are available in the library. So based on that input, the synthesis will design the hardware for you. He will not make anything in random. So it is all dependent on what kind of hardware levels components are available in your library. Okay. So that's why for the synthesis process, having the library input is very, very important and significant. Okay. So having the technology library file over here is important. Now let's take the next step. So once synthesis is done, this guy performs a static analysis. Okay. Anyone familiar with static time analysis? Anyone? Yes, no? Because my chat room is all fresh and clear and wiped out. There's no hi, hello even. So I just want to make sure that I'm audible and I'm not going blank anywhere. What, like I'm not audible? Nihal? Okay. So yeah, anyone familiar with static timing analysis? Anyone who has heard it? Calculating the required delay for timing applications. Okay. Anyone family? No. No issues. Okay. Just give me a minute. Something. Okay. So static timers is a part of the process where you try to identify that at what speed the design can operate. Okay. Now the question comes up that how this is possible, how any software can identify that at what speed the design will operate. So the idea is very simple. Okay. The logic and the idea is very simple. So let's say my synthesis process, I gave him this design and okay, and this is how he implemented also in the same way because he was having two input NAND gates. So he can do this, right? He can also do this, right? It is also possible that he might does this. Isn't it? He might even do that. Okay. Now, let's say the design technology library file has all these components available with it. They also has two input NAND AND gate. They also has two input NAND gate. They also have a NOR gates. Okay, they're all available in the library. So which one he will use? Or if possible that he might also have this one in the library. So he might use any one of them. Okay, so which one he will use? Okay, first of all, let's find out that how the delays are computed. So the library has all these information that let's say this is an AND gate, the delays are 2 nanoseconds. Let's say there is a NAND gate, so it has 3 nanosecond of delays. Okay, let's say I'm going, I think I'm going reverse. So this is 3 input NAND gate, so this is 3, this is 2, this is 2, this is 2, and this is also 2, 2, 2, 2 nanosecond, 2 nanoseconds, and this is 4, let's say. Okay. So which one the design will use synthesis process? Well, it's based on this. So now here, if I see the delay from A to Y is what? 6 nanoseconds, because this is how the delay passes through. This is how my data passes through from here to here, right? So my delays would be, the delay would be 6 nanoseconds. Okay, my delays from all C to Y would be only 3 nanoseconds, but I would be working on the 6 because the designs work on the slowest guy possible. Okay, they don't work on the fastest guy. Now looking at over here, so from here A to Y is 6 and C to Y is 4. Now here again A to Y is 6 and C to Y is 4. Here A to Y is only 4, C to Y is also 4. So in static analysis, this is how it does. The STA is a process in which you can identify at what speed the design can operate by just knowing the propagation delay of the blocks in between the data path. That's it. Okay, so this is how an STA can identify the delays in any data path. Okay, So based on that, they do estimation that your design will work at 100 megahertz, 200 megahertz, 500, 1 gigahertz, based on your application. Okay. Anyone has any doubt or question over here? Okay, no problem. Mm, The next in the stage is once STA is done, okay, you go for the module partitioning. So based on the design requirement and the design related issues, everything is partitioned, okay, based on the constraints, okay. And the entire design is divided into small sub modules so that they can be fitted nicely. In the same manner, your house is laid out, okay. Okay, that you decided that, okay, my house will have 4 bedrooms, one kid's room, one study room, one lobby, kitchen, veranda. I mean, you decide the entire layout of the house. Then you divide the entire house into small blocks and you start thinking that, okay, where and how the entire set would be divided. So they can be fitted into smallest jigsaw puzzle. That's it. So once that is done, you just sign off from the front end and move it to the back end of the design. Okay. In which the first stage comes the floor planning that, okay, the design was partitioned to small parts. Now where they can be fit in the layout. So if you have a given piece of silicon die, how the design blocks will be fitted. Okay. So that they use the minimum size possible and they do not violate any important design or the area constraints. Because in this, everything is based on various constraints related to layout planning and the design issues. Because for example, in case of even your bungalow design, you think not only from technical aspect, you look from the financial aspects, you also even consult Vastu Shastra that, okay, my bedroom is facing towards the east side or west side, or my front face while entering in the home is north facing, south facing, blah, blah. I mean, like there's so many constraints related to planning of the house. But still, anyhow, you have to consider everyone's opinion and advices. And once they are approved, you go for the next stage, which is you convert your design modules into the layout. You convert your actual chips, I mean, like design parts, blocks into the actual running layout. Okay. And when it is done, you go for the placement and routing that actually you start erecting of your house. You give it to your contractor because the backend guy are nothing but the contractor. This entire part is the part handled by the contractor. He's engineer by profession, I agree, but then he's not the architect. Okay. So he just look at your layout plan and he will start constructing your house. Okay. So he does the place and routing. That is, he start putting the components and he start using the metal lines to join the components. Okay. So it is the same way, and here the design rules are different. The design rules followed by the contractor or the design backend designers are different than the front end designer. Okay. What difference are there? The contractor thinks about what kind of wall thickness shall I keep or maintain to sustain the load of the entire building. Okay, what kind of materials I use, in what proportion should I use, okay, so that I make it nice and beautiful and erect walls instead of making some flaws on that. Okay, so these are the rules which an backend designers follows. So they look at what kinds of thickness of the wires or the interconnect materials I'm using, okay, how the components are placed, they are not violating any heat or thermal rules and violations, okay. And now once that is done, after performing some analysis, the design is sent to the foundry guy teams. So these are all manufacturers. These are actually manufacturers where everything is being given to these guys for the fabrication purpose. So they just validate your design file. Are they, have followed any standard, their design kit or not? And they verify that all the transistors which you have used, they are correctly described and properly defined or not. Once that verification is done, the actual manufacturing of the chipset start. So once the prototype testing is succeeded, it is given for the final pilot production. Okay. Now I just left around one middle block in the segment, which is for the verification or the simulation part of it. Okay. So here there are three stages of verification or simulation. I believe you guys are familiar with simulation. Uh, can I have a couple of yes or no that you guys are familiar with pre, post layout simulation, function simulation, or simulation itself? It is for just for my reference to get an idea. You're familiar with simulation. That's great. Okay, that's good. So we can quickly cover that. So as you guys must be familiar that functional simulation is divided into three parts: function simulation, pre-layout simulation, and post-layout simulation. Okay, so in function simulation, the design is verified after the design entry. So here the verification or the simulation is done based on the behavioral simulation of the design. And it is being verified that design is going to work properly, okay, after it is being entered in the design part, either in schematic or Verilog. Okay. Uh, okay. Any doubts in question till here? Okay, just give.
Hello, Vinayji, we are not able to hear. Some audio problem.
The scenario changes when you give a logic high at the input. The PMOS is off and the NMOS is turned on now, and it will allow the capacitor to discharge to ground through itself, making the output going low. Okay, but now in some cases where your input has a slanting rise and fall time, that means it takes a lot amount of time to charge to VCC and discharge from VCC. So what will happen? For a moment, both of the transistors would be in the linear region and they will allow the VCC to short with the ground. Although it is for a very short moment, but it will happen. producing spikes at the output and causing the maximum amount of power supply to be drained straight from VCC to ground. Okay, so this is what happened to it. So these are generally two types of power dissipation: short circuit and dynamic. And in static, when the transistor is not working even, it is just turned off, then also it will consuming power. I asked you guys for give me some real life example where you have seen static power dissipation. Can you tell me any example? Any example where static power dissipation is happening? Not necessarily electric example. You can give anything. Mobile phone. Yes, mobile phone can be a good example. When you're not using the mobile phone, still it consumes some battery, right? That is why when you purchase a mobile phone, they always tell you two types of power consumption in a generic manner, so that a common user can understand it. So they simply say that if you use the phone for talking purpose, if you make calls and talk to a person continuously, so then he will give a backup of 5 hours. So for 5 hours continuously you can talk to the people. But if you don't use the phone and you put the phone aside, keeping it on, so in the standby mode, it will go for 10 days. So this is how they can, compare the power consumption of a mobile phone. You can even take any example, such example where there's active and static power dissipation, even your bike or scooter or a car. So for example, you just turn on your scooter or a bike, okay, you just pull a kick on it, or these days only a button to start the bike, okay. But now you're not using the bike to travel to a distance. The bike is statically holding a position. Now, let's say if you put a 1 liter petrol in the bike, what will happen after a couple of hours? The all petrol is gone. The all petrol is gone for in a 1 hour or 2 hour at the max. Although your bike didn't move a single inch, still all the power was wasted. Okay. So this is nothing but a static power dissipation. Okay. Then glitches gulps power. That's very interesting. Are you guys familiar with glitches? One, no. At least I need 4 or 5 so that I understand the majority of inclination of the audience. Okay, glitches. So for example, you have any logic circuit and the expected output of the logic circuit was high. Okay, let's say this is high and low. But due to some change in input behavior, okay, and the output was expected to be high, but while for a short moment, the output went low and came back to high. Okay, so this is nothing but a glitch. So for a moment, the output changes its states and come back to its desired states. Okay, that is called as glitch. Okay, that is a glitch. Although it may or may not harm your logic. It's not necessary that they will harm your logic. It may or may not harm the logic depending on many other factors. Okay. So, but still this phenomenon is called as glitch. And glitch is something which is like just, changes the state. For example, an output was supposed to be 0, but all of a sudden it comes high and come back to 0. And that happens due to mismatch of the delay. It happens due to mismatch of the delay. Now, what do you mean by mismatch of the delay? What the hell is about mismatch of the delay? Okay. Now, for example, you have you have made some logic generator. So let's say there is some logic generator in which he can identify that if any of the two inputs are logic high, any two inputs are high. Okay. So in this case, the output here is 0, right? So in this case, let's say output y, this is 0 over here, but here it will be 1. Okay. Now let's say that is my next stage. So the output is expected to be 1 only, because at the end of the day, these are two inputs are 1, and here also two inputs are 1. Okay. But let's say another scenario in which he was already at 101 state and the output was 1, but you are changing the inputs, and the person who was responsible of changing the input, he made the input like this. Okay. So before going to 110 for an intermediate time, the A took little bit more time to change its state. Sorry, B took time to change its state for going to 1. So what will happen? For a moment, it will go to 0 and come back to 1. So it was expected to be 1, but for a short moment, it will go to 0 and come back to 1. So this phenomenon will be called as a glitch. I believe I've made some explanation of it. Okay. Any real life example? Yes. Your hiccups, right? Or when you sneeze. Achoo. So you are sitting video games. Yes. I think there was a movie. Raphael, which was that movie? There was a girl who does a car racing. In fact, her name itself was Wreck-It Ralph. Wreck-It Ralph. In that, the girl was called Glitch, right? So she had a tendency of glitching always. Okay. Okay. So, or in case of humans, like when we sneeze or when we cough, so in our static attention position, we have to do a change of state, but we come back to normal. So that is a glitch. In case of bikes, you remember, you just turn on your bike and you leave your accelerator, okay, and then what is happening? The bike is consuming in static power. Now, all of a sudden, the RPM is also constant. The RPM is also constant, but all of a sudden, just due to excitement or anxiety, you put a throttle. Vroom. So what happens? The throttle goes to high and come back to the same state. So that will be a speed glitch where you just change the speed of the throttle of the engine RPM and come back to normal. Now, why we are talking all about this? Because the glitches, they faced power. Remember this. This word is important. They waste power. In early days, in 90s and early 2000, people didn't care about glitches because in those days, the glitch is very small and the power consumption was not that important because in those days, the power optimization was to their best. And the number of devices were not that high. You can easily maintain it. But these days, number of devices are so high and so are the glitches. So what happens, the glitches, if they are generated, although they are not harming your design, they are not damaging your logical output, but they are wasting power. Now imagine you put your bike on a normal throttle, you just turn on your bike, okay, and leave the bike. So let's say it can go for 2 hours. But if you sit on your bike, you're not riding anywhere, huh? You're not going anywhere, but you just keep on doing this vroom, 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 vroom. You just keep on doing glitching, 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 vroom, vroom, like that. So what will happen? So instead of 2 hours, your bike will, burn the fuel in only 1 hour. That's it. So you are wasting your power. Okay. So that's what it is. So glitches is also very important to take care of in these days and address this nightly. Okay, now let's look upon how the power consumption goes up. Okay, so the power is computed by this formula. We have already shared it. Uh, it's FCV square. Okay, so it's the frequency, capacitance, okay, and the voltage. So voltage on which the transistors are working on. Okay, capacitor means the entire number of transistors. Number of transistors in your design. Frequency at which you are working. This is the maximum operated frequency. Okay. So if you know this is the formula for identifying and dynamic power dissipation in any design, okay, so you can go ahead with doing the power optimization. Okay, but you will be surprised to know that which are the power hungry modules in any design. So let's take any microprocessor. So in microprocessor, if I would have asked you that which is the power hungry modules in any microprocessor, probably you would have said execution unit or IOs or timer or interrupt. Okay, but those would have been wrong. The highest consuming guy is clocks, the clock network, because not only they have large network, okay, but at the same time they are switching at every cycle, because the cache memory, they are not updated at every clock. IOs, they are updated at the slowest. I mean, they are the slowest guy to operate, slowest guy to operate. Okay, so the clocks, they consume a lot of power because of the frequency at which they operate. So now if you know this formula, P is equal to FCV square, then how you will optimize your power consumption? So here are some tips and tricks in which you can optimize your power consumption. Let's talk and discuss about it. And I want you guys to participate in this and ask me questions that how this is possible and how that is possible. Or let me know if something is not clear in your head. Because optimizing power is a very, very complex phenomenon, and most of the designers, sometimes they fail to do it. Okay. So power, you cannot reduce the voltage because that is constant figure, right? Because a transistor is operating at 1 volt, will operate at 1 volt. You cannot reduce the voltage. Okay. You cannot, frequency cannot be compromised. Why? What does this mean? Why I cannot compromise frequency? See, every word you can talk and discuss if you wish to. Someone can come on mic and talk also. That is more better. That will be easier. Let me know I was audible throughout, and I didn't miss anything interesting. when I write this, frequency cannot be compromised. Why? Okay, this I explained that when what do you know voltage is constant, because a transistor, okay, let's say NMOS or a PMOS, okay, sorry, this is NMOS, and it's working at a VDD, so that has to be 1.2 volt or 1 volt. So it has to work on that, otherwise it will not work. Okay, you can't change that. Okay, you cannot change that, because for changing that you have to change the technology, which is not possible every time. Then, as we know, P is equal to FC square. So voltage is ruled out. We can look at the frequency, but I say that frequency cannot be compromised. Why I cannot compromise on frequency? Can I have a couple of answers, please? Any participations? Mhm. Mhm. Okay, good. Keep on coming. Keep on answering. You can come on the voice also, audio also. That is more faster. In fact, you can talk longer and longer. Only two answers out of, I think, 27, 28 people. No, the clock synchronize issue is not time period changes, not relative. The clock will have standard frequency, not true. Hmm. Yes. Any more? Any couple of people more at least? Because I got variation of climate. Climate कैसे related है? I mean, how the climate is related? I'm trying to understand that. And wave propagation is affected. Wow, you went into deeper physics. Okay. Hmm. I give you two examples. Okay. I can give more, I mean, but still, to keep the time short. In case of your electronics, let you take any gadgets, your mobile phone, anything like that. Okay. So you have mobile phone one, okay, and you have another mobile phone. There are two mobile phones in your hand. First guy, uh, he operates at 2 gigahertz. Okay, it operates at 2 gigahertz. Okay, and works for 5 days. Okay, then you have another mobile phone which operates at 1 gigahertz and works for 10 days. Here the battery can go for 10 days. 2 gigahertz, 5 days, 1 gigahertz, 10 days. The rest of the features are all same. I mean, same Android operating system, the same number of transistors and same functions, functionality, camera features, all that stuff are same. Which one you will choose? One or two? Is that simple question to answer? One or two? Okay. One got one vote. At least 5, 10 votes I should see so that I can make a judgment. Come on, 5 days battery wala, 2 gigahertz phone, 10 days battery, 1 gigahertz phone. Which one you want? Everyone wants one. No one wants two. Why? There is at least chalo Pooja likes two. That's good, Pooja. Maybe if I change the price tag, then everyone will like the second one. This is on 50% discount, no discount. Okay. Well, it depends. Obviously, yeah, depends. But still, in a generic way, see, no one likes a slower phone. No one likes a slower product. Okay. If both phones has the same features and same functions to operate, but one guy is faster and one guy is slower, no one will get attracted to slower phone. You remember we all think and dream of having a phone which is fastest and having the best functions and who can operate faster. These days we really care about the battery because at par all of them provide the same battery function. Everyone sustain the entire 1 day of work. Okay, so that way it is very good. Okay, so that is why frequency cannot be compromised because frequency is attached to performance. It is like another example. For example, you are a Formula One team. You are a Formula One team, and you observe that after 10 laps, okay, your car comes for refueling. Okay, your Formula One Ferrari car comes for refueling. Okay, after 10 laps, remember that. And you feel that somehow the economy of the car, it's funny, you will find it, but it's important and significant. The economy of the car has to be improvised so that the power consumption has to be optimized of the car, the Formula One car, so that instead of 10, at least it goes 1 or 2 rounds extra. So instead of refueling the car after 10 laps, he should come for refueling after 11 or 12 laps. A simple logic. Okay. So what do you do? Will any of the design engineer will suggest that you just slow down the car? You just run the car slowly. Your fuel will be conserved and you will save the power. Don't you think that everyone will turn around and look at you from where the suggestion came up? Right? And there would be a gunfire probably. And probably you will be thrown out of the team. That this guy can't even think straight. He doesn't even understand what is the requirement. Because how you can, yes, so you can always talk about reducing the weight, reducing the air drag. You can change the materials used in the making of the car, anything else than the speed. Because there is that application, you cannot compromise the speed. The frequency cannot be compromised because reducing the frequency is like impacting the performance. Okay, so no one likes it. So you have to think of smart ideas where you can always conserve power. Okay, so some ideas are like you can change technology, but that is not possible every time. That is not possible. Okay, you can improvise the architecture, which is possible every time, always possible. Okay, you can reduce the node capacitance to reduce the load. You can balance the differential path to avoid the glitches. Okay, you can place buffer at the clock network. Then you can always go for smart clocking in case of wireless or at any network, in which you just turn off the circuits or the part of the chip which are not used by the design. Okay, and then there would be definitely a power conservation. Okay, that's how it is. So even in your mobile phones, you must have noticed that there is smart clocking done in the mobile phone and even in the laptops to conserve power. So for example, when you are not using laptop for a while, it just turn off the screen. And after some time, still if you're not using the laptop, you will find it will just slow down the clock. Okay, he will install, let's say he was working at 2 gigahertz, he will come down to 1.5. And 10 minutes further, still if you're not touching the laptop, he will come down to 1.2 and then probably 1 gigahertz. Okay, he will keep on coming the frequency lower and lower so that he can just conserve the power because no one is using it. Okay, no one is using, and the moment you touch your laptop or you bring back from the sleep state and come back to active state, so all of a sudden he will just multiply the clock and boost up the clock speed so that he can start operating at the highest performance possible. So this is the way, these are techniques and tips and tricks through which you can always improvise the speed. Okay, maybe just let's try to complete this timing issues today, and then we'll see further. Okay. Mm. Timing also is also a very important aspect of chip design. So where you try to identify that at what speed this design can operate and how you can verify this design at the required speeds. Okay, because anything incorrect in timing will definitely land up the entire design into failures. So let's first classify the systems. So generally there are three types of system. One is basic are two, a synchronous and asynchronous system. The third is the hybrid of both. So in synchronous system, everyone works on a global clock signal. Like you must have seen the march past or parade during your Republic Day or even in your schools. So everyone walks with the same momentum. So that is a clock signal. So you have a generic clock signal which has been applied to the design, and everyone operates with the same clock. Okay. So the issues are related to clock skew and jitter that we will talk about later. Then asynchronous, they are self-time control system in which they generally don't pass on the data based on the clock, but they do handshaking and pass on the clock. Okay. Have you guys studied about this asynchronous, synchronous? Because I wish to explain in detail, but then if I go too much in detail, then that will allow the time to kill. Have you guys studied about this synchronous system or synchronous system? Mm-hmm. So Nihal says yes. Anyone else? Yep, studied it. That's good. So I can take something on the higher side. Okay. So asynchronous system, they are self-timed. That means they work on the handshake. So generally synchronous, what happens? It's a pipeline logic. Everyone does the work at a given time frame. That let's say if the system is operating at 100 megahertz, so your clock speed is, the clock period is 10 nanosecond. So every block gets 10 nanosecond of time to complete the job. Okay. So 10 nanosecond काम हो गया, push the data forward. 10 nanosecond work done, push the data forward. But in what may happen that someone may be slow, someone may be fast, some block. So in synchronous system, but this will not matter. Everyone will move at the same speed. But in some cases, it might be slower. So asynchronous, what happens? They pass the data when their job is done. So if I process the data, I just send an interrupt to the next guy, and then he picks up my data and starts processing. And I take the next data and I start processing. So this is handshaking. So, but then it is very complex to write logic or design something of asynchronous. Okay. Synchronous systems are very easy to design and comfortable to work with. So clocking is also a huge problem in the chip design because you have such a millions of transistors in the entire chipset, and then you have to make sure that the clock reaches to each and every corner of the chipset and reach properly, maintaining all the issues related to skew and jitter. You guys familiar with skew and jitter? You guys familiar with skew and jitter? Okay. Uh, mm, so what happens is, let's say this is your clock, and due to delay, So this is clock 1, this is clock 2. Let's say you have some design in which the clock enters from here, the clock 1 enters from here, okay, and it comes to this block. Then what you do is that you just put some buffer on the clock and give it to another module, and this is your clock 2, okay. So what will happen, the same clock edge, you know, this is the same clock edge, so this is the same clock edge reaches to a different chip point, okay, at a delayed, okay. So it's the same clock edge is delayed, okay, because of the buffers in between or due to the transmission lines, okay. So this delay is called as skew. This is called as skew, okay. This is called as skew, okay. Then secondly is jitter. Jitter is nothing but clock cycle to clock cycle difference. So it might be smaller. So you say due to some, you know, voltage fluctuation or the current fluctuation, the duty cycle changed. So let's say this was 10 nanosecond, 10.0 nanosecond. This is like 9.98 nanosecond. So it is like clock cycle to clock cycle variation, change of period. Jitter. So from clock cycle to clock cycle, the clock period is not constant. The clock period is changing, varying. Although it is varying by a very, very small margin, but this is possible because of change in voltage, change in current, or change in load. This is all possible. So that is called as jitter. Okay, it is like shivering of the clock. Many of time people call it that my clock is shivering. Okay. So there are two types of analysis method. One is STA and another is DTA. Okay. So static dynamic analysis is a technique in which you just identify the maximum operating frequency in a circuit. Okay. So this is a technique in which you just identify the maximum operating frequency in a given circuit. Whereas in a dynamic timing analysis, you just simulate the design at that given frequency and verify that this will work nice. So let's take something good. Can I fill up the table in this? Okay, not sorry. So how many data paths are there? This is A to Y, A to sorry, A to Y, right? Then I have B to Y, and I have C to Y. Can you guys tell me what is the delay between A to Y? 2 nanosecond is the delay of each block. Okay. What is the delay of B to Y? C to Y, what is the delay value of C to Y? That's good. Now you guys tell me, did you apply any logical input to find these values? Did you apply 0, 1? Did you even saw that this is AND gate, NOR gate? Now, if I change this to NAND gate, will it make any difference? No, doesn't matter. I just need to know that what is my timing path. So these are called as timing paths. These are called as timing path. What are timing paths? start and end point of data flow. In this case, the start point is A and end point is Y, because the data will start from A and end at Y. In the second case, it will start from B and end at Y. Third case, it will start from C and end at Y. That's it. I just need to know what are the timing paths, not the data paths actually. I need to know the timing path. Okay. Whereas in this case, for example, I have some logic like this: A, B, and this is C, let's say, and there is a flip-flop, and this is Y, and this is clock. Now, can you guys tell me the timing paths in this case? There would be A to D, B to D, C to D. Now you may ask me, sir, why not Y? Why this is not Y? Because my final output destination is Y. This guy is going out of the chip. Why not I'm using it Y? No, because what if I give any data here? I change any data here from, let's say, 0 to 1. Will it reflect at the output Y immediately or even after some delays? No, it won't. It will not, the output will not be changed until unless there is a change in the clock. So these two are related. These two guys are related. Okay. So that means my data will start propagation here and will terminate over here. Right? So it will start at A and end at the D input. This is also called as setup because this is setup input of the flip-flop. So A to setup and B to setup and D to setup, I mean C to setup. Then I have another timing path which is clock to Y. Because if I give a data or a clock pulse here, the data will start from D, although it will start from D. But see, the timing is from clock. You know, it is like I just fire a pin, and then the bullet goes out. Because I'm pulling the trigger, but the bullet is coming out. Trigger is not coming out. Okay. So when I give a trigger, okay, the data from the D starts propagation and come to Y. So I'm just observing the tick given at the clock and the timing arrival at Y. Okay. So let's say this value is 4. I mentioned this as 4. The rest of the values also remains 4 here. And let's say for clarity, let's say it's 6. You know, just so that we don't get confused. That why all are 4. So here the timing path is clock to Y. So this is called as timing path. Okay. So in this case also, I have to just know the delay values from clock to Q, which is 6 maybe. Did I applied any inputs to it, logical 0, 1, 1, 0? No, nothing. It is like, I believe, for example, I ask any one of you that how much time it will take me to travel to the railway station. So that's very simple. You just know that, okay, how far the station is, let's say 10 kilometers. So let's say if you go 10 kilometers hours of speed, so you will take 1 hour to reach. Simple as that. But let's say the city is Bangalore. You have to take factors into the account. Okay. Then what? So that's a different scenario, but at least on paper, the Google will tell you that you might take 1 hour to reach. Now, how does the Google tells it? The Google just take the distance into account and he takes the standard 40 kilometers per hour of speed as an average, and he does all the math. Simple. Okay. So same as the STA. Where is my slide? Yeah. So that's why STA is a static. So here you need not to apply any 1, 0. You just need to know at what frequency a circuit will operate. Okay. Whereas in DTA, you actually verified that when you check your Google that, okay, it will take 1 hour to reach the railway station. Then actually you travel to the railway station and you see that does it correct or not. Okay. So then you may find it due to many other factors. Your values are not 1 hour, it might be 1 hour, 20 minutes, or maybe even 50 minutes, depending on the traffic conditions. Okay. So depending on various factors, your simulation may be impacted. So in dynamic timing analysis, you actually apply the test factors at that speed and you verify the design again at a given your desired frequency of operation. Okay. Then I wish to talk about the maximum operating frequency. You must have seen many of your chipset, they come with a label that I can work at 1 gigahertz or maybe 100 megahertz or 2 gigahertz. So don't you think that this is interesting to know that how do they calculate the maximum operating frequency? Isn't it? How do they operate the maximum operating frequency? So this is done on this timing path. So this is one timing path in any design, in RTL design also, okay, which is called as clock to setup. Okay, so it starts from the clock pin of the first stage flip-flop and ends at the D input of the next stage flip-flop. Okay, so the delays are like clock to Q delay of the first flip-flop. Okay, any combination logic delay in between, which is called as propagation delay in between, and the setup time of the next stage flip-flop. So if you add all these three factors, then based on this, the maximum operating frequency is established. This is the maximum frequency or minimum period or the maximum frequency. Okay. Any doubts on this? I'm not sure how much you guys have digested this logic, because this requires a lot of attention and it takes some time to go through down the throat. And okay, let me ask one simple question. Are you guys familiar with setup time and hold time? What is setup time, hold time? Are you guys familiar? Can I have you yes, no, or if you just remember that I heard it, then say no. Only with distinct yes, you understand. That's good. I found a couple of yes and yes. Okay. It's coming 50-50. Why it is 50-50? I mean, like, either it should have been 80-20 is good, because 20% are who don't study in the class. That's it. But how come 50-50? Okay. So can anyone tell me what is setup time? You can come on the audio because it might be a longer answer to write down. You guys can come on the audio and explain. That will be more easier and faster. No one? Okay, let's do one thing. As the time is also up, I just put this as an assignment. Okay, and maybe in the next class we'll talk from here. Okay, so I just put the note. Okay, so today's assignment is just study about setup and hold time and flip-flop.
Vinayji,
Yes, sir.
what I'll do actually, I have created a WhatsApp group.
Okay.
I'll include your name also if it is required.
Okay.
Okay, and also as no last batch we have done, all the assignment can be uploaded to that particular drive.
Okay.
And any questions, students, you can ask in one of the one-word file, so that anybody can understand that the same answers.
Yes, in what order we are going through. Yes.
Yeah.
That'll be good. So as of now, I'm just putting a steady assignment. As of
Yeah.
now, we are not starting the practical assignment, hands-on assignment. So this is what we start with, okay? And I think that will be good because from next class onwards, I expect we will start with the software. And I also shared the installer link and the software license file. So you guys, in the meanwhile, you can just install the license. So just download this license file and also the MICROWIND link. Okay. Download, install, open the help menu, and go to register, load this license file. Okay. So I've shared the download link of the software, so you guys can download the software and install it, put the license file attached to it. And probably I look forward that from the next class, we can start with introduction of the software tool. And I will give you some overview on the software features and basic operation of the software by next class. And further ahead of that class, we will just do hands-on. That's it. Okay, we'll just do practical and practicals. We'll keep on picking up various topics and keep on doing that. Okay. In the meanwhile, if you have any doubts as of now, you're most welcome to talk about it. No? Okay. Fine, guys. So it was good to be with you all today. And I look forward in the next class. Sir, when we are expecting the next class?
Monday.
Yes, because tomorrow here also we are having a holiday.
Festival, yeah.
Okay. Yeah, festival time. Pune, you understand,
Yeah, yeah.
Ganpati festival is crazy people here. Crazy. Okay. Okay, sir. Sally,
Yeah,
bye
thank you.
everyone. Thank you. Bye-bye.
Good day.